So, in the last class we studied Shannon's first theorem, which provides the fundamental limit on the representation of the data which is being generated by information source. What it said that for a discrete memoryless source, the average length of the source code which you could have has to be always greater than or equal to the entropy of a discrete memoryless source. And we also mentioned that one of the requirement of a source encoder is to provide a uniquely decodable source code. By this we mean that given the output binary stream from the source encoder, I should be able to uniquely decode source symbol sequence from the discrete memoryless source which is input to the source encoder. Now, today we will study the properties of the source code which will satisfy this requirement of the source code to be uniquely decodable. So, let us take an example. I have a source alphabet given by 3 symbols with the probabilities as specified here, and I have shown 6 codes which we can design for this source alphabet. Now, if you take the code 1, we will see that basically there is a problem with this code in the sense that when I receive binary sequence 0 0, I am unable to decode it because there is a confusion whether it belongs to S0 or S1. So, this is not acceptable. The first requirement on a source code is that the code words should be distinct. So, this is not acceptable code 1 because the code 1 for symbol S0 is 0 0 and the code word for S1 is also 0 0. So, code 1 is ruled out. Let us take the code number 6. It appears that the code words are distinct, but again there is a problem with this in the sense that if a sequence of binary stream is available at the output, I am unable to decode it unambiguously. Let us take an example. Let us take say example, I have a binary sequence at the output of the source encoder as follows, and if we try to decode and if we know that this has been encoded using code 6, then there is a problem because 1 I can decode it as 0, 0 1 I can decode it as S1, but there is a problem. I do not know whether it is S0 followed by S0 or it is just S2. So, this is ruled out. If you look at code 3, again the same problem arises, correct. Though the code words are distinct, but when these code words appear in a sequence, it is not possible for me to decode it unambiguously, correct. So, this is ruled out. Then let us take, so this and this are ruled out. Let us look at the code 2, code 4 and code 5. If you see basically again the code words are distinct. So, by the first requirement this should be acceptable, and let us see basically what happens when I get the binary stream at the output of the encoder and see how we are able to decode it. Let me take an example. Suppose if I were to use code 4 and encode S0, S0, S1 and S2, I would get the output as 1 1 1 0 1 0 0 if I use code number 4, and if I use code number 5 for the same source symbols sequence, I would get this as 1 1 0 0 0 1. Let us see the difference between the two. If we observe the difference, if you look at the binary stream, when I get 1 here, I cannot immediately, can I immediately decode this? I cannot, because I do not know whether this is the end of the code word for the symbol S0 or it is basically the first symbol of the code word S1 or S2. So, I have to wait for the next symbol to arrive in this. So, I will not be able to take the decision, but once this one arrives, I can decide that this is equal to S0. And then I come to this symbol, again I cannot decide unless I have observed this next symbol in this sequence. So, then I will be able to decide S0, and then basically when I do this, basically I will get this, I get this, again I will have to wait here, and then again I will have to wait here to see whether it belongs to S2, and only after this has arrived I can decode this as S1, and finally I will decode this S2. So, what happens basically in this case, I need to wait for the future symbol to arrive to decode my present code word. But let us look basically at the same sequence using the code 5. If I do this, basically when 1 arrives, I know basically that this is the symbol S0. When this again here arrives 1, I know it is symbol 0. When this arrives 0, I know that this cannot be a code word, I have to wait for the other thing, I am sure about that, correct. So, basically I wait for the next symbol to arrive, and I know the length, I am also given the maximum length which a code word has in the code, I know it is 2. So, once I know this, basically at this point itself I decide that this is equal to S1, and if I look here, basically this I know that it is the start of a code word, and here basically I know it is the end of the code word, and this has to be S2, correct. So, you see basically here basically this ones, they serve as the some kind of a signaling for the end of the code word, and the length also helps me to decide the end of the code word. So, this is the difference between code 5 and what was the code 4, correct. And if you see the code 2 also, basically I can immediately decide which symbol has arrived after I have observed for 2 signaling intervals. Okay. So, this code, though acceptable for, it is I have to wait for the future symbol to arrive. So, this is uniquely decodable, but not instantaneous, whereas code 2 and code 5 are known as instantaneous codes. They are also known as prefix codes. This instantaneous or prefix code have very interesting property. So, what is that property? To understand that, let me understand the way the code words are formed. So, I have a symbol Sk, and to this basically I have assigned a code word Ck, and this Ck is nothing but a sequence of binary symbols. So, I call Bk1, it could be 0 or 1, then Bk2, the second symbol in this sequence corresponding to the code word Ck, correct, and I have this. So, I am assuming that the length of this code word is equal to n. Now, in this code word Bk1, Bk2 up to Bkj, for j less than or n, for j less than n, this is known as the prefix of the code word, correct. So, Bk1 is the prefix of this code word, Bk1, Bk2 is also the prefix of this code word, Bk1, Bk2 up to Bk3 is again a prefix of this code word. Now, One of the property which instantaneous or prefix code should satisfy in order to decode the sequence instantaneously is that no code word in the source code is a prefix of another code word. So, if you have this condition satisfied, then that source code is known as a prefix code, and once we have a prefix code, we will be able to decode the output sequence instantaneously. And there is another important property which all this prefix code satisfy, and this condition is basically on the length of such codes. So, we mentioned that this code words have the length Lk, then we can show that summation of 2 raised to minus Lk, k is equal to from 0 to capital K minus 1 will be always less than or equal to 1. It can be shown that this is a necessary and sufficient condition for the existence of a prefix code. So, this condition is basically on the length of the code, correct. In fact, so this is known as Kraft inequality. Remember, instantaneous code is a subset of a uniquely decodable code, and later on this property was also extended by McMillan to uniquely decodable code. So, for uniquely decodable code also this condition is satisfied. So, sometimes this condition is known in this inequality is known as Kraft-McMillan inequality. So, what it says that if you take this source, then it says that for this source statistic there is a code word available with length 1, 2 and 2, and you can prove that this will turn out to be, if you just take the, so you will get 1 by 2 plus 1 by 4 plus 1 by 4, that turns out to be 1. So, this means the length will satisfy the Kraft-McMillan inequality. So, there should exist a code of length 1, 2, 2. Correct? Correct? And you see that basically I could design that code in the form here. So, this is the instantaneous code which I could design. Okay. Now, we will use this Kraft-McMillan inequality to prove the following version of the lossless source coding theorem, which applies to codes that satisfy the prefix condition. And what it says is that given a source which is a discrete memoryless source with finite entropy Hs and output symbols with the corresponding probabilities, it is possible to construct a code that satisfies the prefix condition and has an average length that satisfies the following inequalities, correct. So, let us see how to prove this, correct. So, to establish the lower bound, we will note that the code words have the length Li for I greater than equal to 0 and less than equal to k minus 1. So, let us take this difference Hs minus L average, which is nothing but minus pi log to the base 2 pi minus pi Li I is equal to 0 to k minus 1. I can simplify this as follows. I have written Li as minus of log 2 of the quantity 2 raised to minus Li. So, this I can rewrite as now, we will use the inequality log x less than or equal to x minus 1 for x greater than or equal to 0 in the above equation 1, and if we do that, what we get is as follows. Now, so from this expression and using the Kraft-McMillan inequality, if your source code satisfies Kraft-McMillan equality, and this has to be satisfied for uniquely decodable codes or for that matter prefix code, this quantity will be less than or equal to 1. So, what it implies that this quantity is less than or equal to 0, correct. So, this implies that your L bar has to be always larger than Hs. Okay. So, now in this case we know that equality will hold only if this quantity is equal to 1, correct. What will happen is that I should have my pi to be of the form 2 raised to minus Li for all i's satisfying this range. So, it means that my pi will be of the form 1 by 2 alpha I, where alpha I is a constant. So, if alpha is a constant and pi is of this form, then I can choose my Li to be satisfying this equation, and then I will get equality, correct. And in that case the average length will turn out to be equal to exactly the entropy of the source. Now, let us try to establish the upper bound, and that can be done as follows. So, we know that this Li's, which are the length, have to be integers. So, what we do is that we select Li satisfying this constraint. Okay. This is because pi is not of the form 1 by 2 raised to some integer. So, if that is not true, then you will have to choose your Li in another manner, and this is what we are saying, that you choose your Li to be of this form, and then we can show that this will, if you take this Li following this inequality, then I should be able to generate my prefix code as follows. So let us take your Li is larger than equal to log of py. So, this implies that minus Li is less than equal to log to the base 2 pi. So, this implies that 2 raised to minus Li is less than equal to pi. So, this implies that summation of 2 raised to minus Li I is equal to 0 to k minus 1 is equal less than equal to summation pi I equal to 0 to k minus 1, and this is equal to 1. So, what it implies that if I choose this inequality which is satisfied by Li, then I will get this result that 2 minus Li I is equal to 0 to k minus 1 is less than equal to 1. And so, if this condition is satisfied, we know that we can generate a prefix code, correct. So, it is reasonable for me to assume this choice of Li. So, if this choice is acceptable now, so if this is acceptable, then I can see that if I have satisfied this constraint, then multiplying by pi throughout and summing up over all i's, I will get it as so, this implies that my Hs is less than equal to L bar is less than equal to Hs plus 1. So, I have proven this inequality. So, the length, average length will be away from the entropy of a discrete memory source by just 1 minute. Okay. Now, this relationship establishes the fact that the variable length codes that satisfy the prefix condition are efficient source codes for any discrete memoryless source for source symbols which are not equiprobable, correct. Now, in the next class we will demonstrate an algorithm to construct such codes. Okay. Thank you.